So next up, we're going to have Manami Sasaki, who will be talking about the hot interstellar medium in nearby galaxies. Probably. Oh yeah, she will be. Great.
Okay, so hello everyone. My name is Manami Sasaki. I'm from the University of Tuebingen in Germany. And I believe that most of you don't know me. I guess that's the main reason is I do something different than what most of you do. It's high energy astrophysics. And it's my great pleasure to be here, honor also, and to present the optical observational studies of the interstellar medium at high energies. Let me start by showing you this image. You have seen similar. Is that mic on? Is the mic on? Okay. You have seen similar images already many times at this meeting, and for me, as a mainly X-ray astronomer, this image actually looks quite incomplete. And what I mean with that is, if I had to create such an image, it would look like this. So what you're missing here, what you were missing here, are the massive stars that make the stellar winds, heat the interstellar medium, ionize the medium, and then die in supernova explosions, which again drives strong shock waves into the interstellar medium, which is also a source of energy and matter. And then since you have stars usually formed in associations and clusters, these events occur correlated in space and time, which means that at the end you will get something like this, which are called superbubbles, so big structures with diameters of 100 or even up to 1 kiloparsec. And all these structures are filled with very hot gas, shock ionized gas with temperatures of 10 to the 6 to 7 Kelvin. And this is what I'm going to talk about. And the problem about the study of these objects is that they're mostly soft X-ray emitters, which means that the emission is absorbed very quickly. So it's difficult to observe these objects in our Milky Way, and we have to go beyond our galaxy. That's why I will be talking about the study of nearby galaxies. And the best target is the Large Magellanic Cloud, which you see here in the optical. So you see the nice distribution of the stars and the H2 regions, some supernova remnants. And if you look at it in H1, you see the distribution of colder gas. We have seen such an image already today. And then if you look at these galaxies in X-rays, you see diffuse emission diffuse X-ray emission, soft X-ray emission filling the entire disk. Also, in particular, the regions where you have these giant, supergiant shells, and all these shells are filled with 10 million to 10 million Kelvin gas. This is what we got in the 1990s using ROSAT. Since then, we have been able to use better telescopes with XMM Newton and Chandra. We now have better data with higher spatial and spectral resolution. So we have been performing a survey of the LMC with XMM Newton. So that's what we see now. You nicely see these structures of diffuse X-ray emission and also see some prominent substructures. In particular, I want you to look at this region. This is the Tarantula nebula. So that's the 30 Doradus region, where you have active star formation going on, and also a lot of other sources like this or this, which are superbubbles or supernova remnants. So studying these galaxies or these objects in X-rays, we can study the physics of this plasma. And I want to show you one example, which is the H2 region N206, which was identified as an H2 region here, like in images like this in an optical. This is a composite image of the narrowband image taken in the optical, and you can nicely see the H2 region and an additional supernova remnant. And if you look at the same position in X-rays, what you see is the bright supernova remnant, but then you also see some diffuse emission that's well correlated with the H2 region. This is the hot gas inside this superbubble. We can also look at the distribution of the colder gas, like in H1. So this red circle shows you the extent of this H2 region. The green circle shows you the extent of the brighter X-ray emission here. And what we see here is that this entire structure is nicely embedded in a hole in H1. But we, in addition, also have a density gradient to the north. And along this density gradient, there is also a hole up here. And that's what we also see here in X-rays. So there seems to be some gas that's escaping out of the superbubbles. So by studying these objects in X-rays, we can study the thermal emission of the plasma, and we can also get temperatures, densities, abundances. And you get spectrum like this. So this is a completely thermal, typical spectrum of a hot gas. In addition, we can also study the stellar population in this region. And we can make some calculations of the energy input or the mass input. So here, for example, we have studied the stellar content in this H2 region, and can make estimates of the input from the stellar winds, and also how many supernovae must have occurred inside such a superbubble. Now I would like to talk about another special case. You might remember this. This is the 30 Doradus. And this image is actually the first look image of XMM Newton. So it was the first image that XMM Newton took during at the beginning of the mission. And this is a quite interesting region because you have a pulsar wind nebula here. You have this ring-like structure here. You have supernova 1987A, which is so interesting source itself because it's the explosion of a core collapse. It's a core collapse supernova. I would like to talk about this source. Why? Because this image that I'm showing here is a 3-color image created out of 3 X-ray bands, which means red is softer X-rays, green medium X-rays, and higher energy X-rays in blue. And typically, if you have superbubbles or supernova remnants, you would expect them to be yellow or greenish. So it's softer X-ray emission, which is typical for thermal X-ray emission. But this ring-like structure is very striking. It's blue, which means that it is mainly emitting in hard X-rays. So since this object was located close to supernova 1987A, was observed many times with XMM Newton, we had a lot of data and could make a morphological and spectral study in detail. Here on the right-hand side, you again see an optical image of this region, and this ring-like structure is also well shown in the optical So we performed the spectral analysis in different regions, and what you see is, in particular, you have this spectral shape, which is typical for a power law. So this is the spectrum that I'm showing here are all convolved by telescope response, which means, is this microphone working?
Yeah, we
no,
can't
right?
hear you now. I wonder if the mic.
Yeah, I don't know, because.
Can I see the box?
Yeah, I think it's not. Oh, no, it's working. Okay. Maybe I should not stand here. Okay, so yes, I was going to say, if you see a spectrum like this, it's a power law, even though it doesn't look like a power law, and that's because it's folded by the telescope response. And this is a typical emission that we find everywhere in this in this source. But if you go to this side, to this eastern side, what you also see is some additional softer emission with lines, and that's typical for thermal X-ray emission. And so, looking at the eastern side of this emission, we can study the thermal content, the thermal property of the gas, and we actually get some temperatures. We see what the property of the plasma is, and then we can also get some estimates of the element abundance. And in this particular case, we got some overabundance of oxygen, neon, and magnesium, which is indicative of a core collapse remnant. Now to the bluer emission, the power law emission. This is, as I said, a component that we see everywhere in this source. And since we believe this non-thermal emission is coming from the same particles that also produce radio emission, we measured the flux and extended this SED down to radio, where we had the radio data. And we nicely get a consistency between the radio and X-ray emission. So this shows you that this hard X-ray emission that we see everywhere in this ring-like structure is most likely a synchrotron emission, and the shape of the object is just limb brightening. So there are particles that's accelerated in the outer parts, and something like this is very unusual for superbubbles. The only other object that has a similar characteristic is the H2 region in M33. This was also observed to have hard X-ray emission. So these two superbubbles are the only known superbubbles that show synchrotron emission, and we believe that this is caused by particles accelerated inside the superbubble. But the problem is, if you have an object like a superbubble, because it's filled by very thin gas, typically if there is a supernova remnant, which should create a strong shock, dies very quickly. So there is not a very good physics or mechanism that accelerate particles, but you need the particles, the relativistic particles, and also the enhancement of magnetic fields. So what we believe, based on these observational data, is that there must be some mechanism going on that enhance magnetic fields and also create magnetic MHD waves that can accelerate particles to such high energies. So, yeah, that's the end. Just one example. We have very recently discovered another case where we have where we had a supernova remnant, which you can see in the soft emission. In this remnant, we found some hard X-ray emission. And this X-ray emission, hard X-ray emission, was found right at the position where the supernova remnant seems to hit an H2 region, which is shown here. And this source was observed 2 times. And you see that the hard X-ray emission seems to be variable. And a variability in such an emission is also indicative for change in the magnetic field. So now we have 3 sources that look interesting in terms of magnetic field amplification. And this is now the end of talk. It's just a summary that we study supernova remnants and superbubbles to learn about the hot phase of the interstellar medium. And typically, these sources are thermal X-ray emitters, but in some cases, we also detect non-thermal X-ray emission, which will help us to understand the particle acceleration and magnetic field amplification. Thank you.
I think I have time for one quick question at the back there.
Very quick. What's the size of those three bubbles? Linear size?
Typically, like tens of parsecs.
Tens?
Yeah.
Okay, fine.
All right, let's thank our speaker again.